Imagine a place in the universe where space is so curved that not even light can escape, a black hole. For decades, physicists, myself included, have debated whether these cosmic enigmas erase information forever. Stephen Hawking famously argued they do, suggesting a kind of cosmic amnesia. But what if that's not the case? What if the universe, in its subtle mathematical elegance, preserves the information hidden in ways we are only beginning to understand? Today, I'll walk you through why, after 30 years of thought, debate and calculation, I am convinced black holes do not destroy information, and why winning this bet with Hawking has profound implications for our understanding of physics. Black holes are not merely exotic astrophysical objects, they are the crucibles in which our understanding of the deepest laws of nature is tested. When matter falls into a black hole, classical general relativity suggests it disappears beyond the event horizon, taking its information with it. Yet quantum mechanics, the theory governing the microcosm, insists that information cannot be destroyed. Reconciling these two frameworks has been one of the most persistent challenges in theoretical physics, known as the black hole information paradox. Over the past 3 decades, my work has explored the mathematical structures of spacetime and quantum theory, searching for a coherent resolution. By examining the subtleties of quantum field theory near event horizons, the properties of Hawking radiation, and the intricate geometry of spacetime singularities, a picture emerges. Information may not vanish as once thought. Instead, it could be encoded in correlations within the radiation, or in ways that require a more nuanced understanding of spacetime itself. In this lecture, I aim to present these ideas with precision, distinguishing what is firmly established in peer-reviewed physics from ongoing speculation, and to explain why the information loss paradox may be resolved without violating the fundamental principles of quantum mechanics. The black hole information paradox arises from a profound tension between the two pillars of modern physics, general relativity and quantum mechanics. According to Einstein's general relativity, a black hole forms when a sufficiently massive object collapses under its own gravity, creating a region from which nothing, not even light, can escape. This region is bounded by the event horizon, beyond which classical physics predicts that all details about the matter that fell in are irretrievably lost. In this classical picture, the singularity at the center of a black hole represents a breakdown of spacetime itself, a point where densities become infinite, and the laws of physics as we know them cease to operate. Quantum mechanics, in contrast, is founded upon the principle of unitarity, which asserts that the evolution of a closed system is reversible in principle, and that information about its initial state cannot be destroyed. When Hawking introduced the notion of black hole radiation in the 1970s, a subtle paradox emerged. Hawking showed that black holes are not entirely black but emit thermal radiation due to quantum effects near the event horizon. Over immense timescales, this radiation causes black holes to evaporate completely. The radiation is largely featureless and depends only on the macroscopic parameters of the black hole, such as its mass, charge, and angular momentum, rather than the detailed quantum state of the matter that originally formed the black hole. This suggests that as the black hole disappears, the specific information about the initial particles is lost forever, seemingly in violation of quantum mechanics. The paradox is sharpened when considering a sufficiently large black hole, which could exist for billions of years before evaporating. The question then becomes whether the apparent loss of information represents a fundamental breakdown of quantum theory, or whether there exists a subtle mechanism by which information is preserved, albeit in a form that is extremely difficult to reconstruct. Resolving this paradox is not a matter of philosophical preference, but is essential to maintaining the internal consistency of physical laws. It challenges our understanding of space-time, causality, and the ultimate limits of predictability in the universe. The paradox has motivated extensive research into quantum gravity, holography, and the microscopic structure of black holes, highlighting that any complete theory of nature must reconcile these apparently contradictory aspects of reality, preserving the unitarity of quantum mechanics, while accounting for the extreme geometries predicted by general relativity. Hawking radiation represents one of the most remarkable intersections of quantum mechanics and general relativity, revealing subtle effects that occur in the extreme environment near a black hole's event horizon. In classical general relativity, black holes are perfectly black, emitting no energy and trapping everything that falls into them. However, when quantum field theory is applied in the curved spacetime surrounding a black hole, a new phenomenon emerges. The vacuum is not empty, but seethes with transient quantum fluctuations, where particle-antiparticle pairs spontaneously appear and annihilate almost instantly. Near the event horizon, one of these particles can fall into the black hole, while the other escapes to infinity. The particle that escapes is observed as radiation, now known as Hawking radiation. This radiation carries energy away from the black hole, leading over incredibly long timescales to its gradual evaporation. Importantly, the radiation is thermal in character, resembling black body emission, with a temperature inversely proportional to the mass of the black hole. Smaller black holes are therefore hotter and evaporate more quickly, while large astrophysical black holes emit radiation at temperatures far below the cosmic microwave background, making the effect extremely difficult to detect. The key insight of Hawking's work is that black holes are not entirely isolated. Quantum processes allow them to interact with their surroundings in subtle ways. While this radiation implies that black holes have a finite lifetime, it also raises profound questions regarding information. The radiation appears to carry very little information about the matter that initially formed the black hole, suggesting that as the black hole evaporates, the detailed quantum states of infalling matter may be lost. This is the essence of the information paradox. Yet the process of Hawking radiation is not arbitrary. It is governed by precise mathematical relationships derived from quantum field theory in curved spacetime. The predictions have been verified in analog systems such as sonic black holes and condensed matter experiments, which reproduce similar quantum emission processes. The study of Hawking radiation has driven much of the research into the microscopic structure of black holes and the search for a quantum theory of gravity, as it provides a rare window into how quantum effects manifest in regions of extreme curvature. While some aspects remain speculative, the existence of Hawking radiation as a fundamental quantum effect is widely accepted within the physics community, forming the foundation for modern discussions about black hole thermodynamics, entropy, and the ultimate fate of information that enters a black hole. Unitarity is a cornerstone of quantum mechanics, representing the principle that the evolution of a closed quantum system is reversible and that information about its initial state is never lost. Mathematically, this is expressed through the unitary nature of the time evolution operator, which preserves the total probability of all possible outcomes. In practical terms, if one knows the complete quantum state of a system at one moment in time, one can in principle reconstruct its state at any past or future time. This principle underlies much of modern physics, from the behavior of fundamental particles to the consistency of quantum field theory. The challenge arises when considering black holes within this framework. Classical general relativity predicts that matter falling into a black hole disappears beyond the event horizon, leaving only mass, charge, and angular momentum as observable parameters. Hawking radiation, while demonstrating that black holes are not completely inert, appears to be largely featureless, encoding only macroscopic properties, rather than the detailed microstates of the infalling matter. If the black hole evaporates completely, the final state of the radiation seems independent of the initial conditions, implying a non-unitary evolution and a fundamental violation of quantum mechanics. Resolving this tension requires reconciling the classical picture of black holes with the unitarity demanded by quantum theory. Various proposals have been explored, including the idea that information is somehow preserved in subtle correlations within Hawking radiation, or that new physics at the event horizon allows information to escape. These possibilities are not speculative in the sense of being untested. They arise from rigorous mathematical considerations of quantum field theory in curved spacetime and from attempts to extend unitarity to gravitational systems. The importance of unitarity extends beyond black holes, as it ensures the internal consistency of quantum theory itself. Violating unitarity would undermine fundamental concepts such as probability conservation and predictability, calling into question the entire structure of quantum mechanics. Consequently, the insistence on unitarity guides theoretical investigations into quantum gravity, holographic dualities, and the microscopic description of black holes. By maintaining the principle that information is never truly lost, physicists can explore models in which black holes conform to both general relativity and quantum mechanics, suggesting that the apparent paradoxes are a reflection of our incomplete understanding, rather than a fundamental flaw in nature. The reconciliation of black hole behavior with unitarity remains one of the most profound and active areas of research in theoretical physics, pointing toward a deeper comprehension of the universe at its most extreme scales. The mathematical structure of spacetime lies at the heart of understanding black holes and the information they may encode. In general relativity, spacetime is not a passive backdrop, but a dynamic entity shaped by the distribution of mass and energy according to Einstein's field equations. The curvature of spacetime governs the motion of matter and light, and in extreme cases, such as the formation of a black hole, this curvature becomes so pronounced that it produces an event horizon, a boundary beyond which classical signals cannot escape. Roger Penrose's work on the global structure of spacetime, including the development of Penrose diagrams and the concept of singularities, provides essential tools for visualizing these extreme geometries. These diagrams compactify infinite regions of spacetime, allowing physicists to trace causal relationships and identify how information might propagate even in the presence of singularities. Singularities themselves, though mathematically predicted to possess infinite density and curvature, are often viewed as indicators that classical general relativity is incomplete and must be reconciled with quantum theory. The fine structure of spacetime near and within a black hole may encode information in ways that are not immediately apparent from macroscopic observations. Subtle correlations in the quantum fields, entanglement across the horizon, and the geometric properties of spacetime all suggest that the apparent loss of information could be an artifact of interpreting the system purely classically. Furthermore, concepts such as the holographic principle, inspired by string theory and quantum gravity research, posit that information within a volume of spacetime might be entirely represented on its boundary, the event horizon itself. This aligns with the idea that the geometry of spacetime carries information in a non-local way, where the curvature and topology encode far more than what is visible through classical measurements. The interplay between geometry and quantum mechanics also appears in studies of black hole entropy, where the area of the event horizon is proportional to the information content, indicating a deep connection between spacetime structure and the microscopic states that constitute a black hole. By examining the precise mathematical frameworks of spacetime, including conformal structures, causal relationships, and singularity theorems, physicists gain insights into how information may survive even under conditions of extreme gravitational collapse. In this sense, the study of spacetime geometry is not merely an abstract mathematical pursuit, but a key to resolving the information paradox, providing a rigorous foundation for understanding how the universe preserves information in its most extreme environments. Several mechanisms have been proposed to explain how information may be preserved in the presence of black holes, each emerging from careful consideration of quantum mechanics and the geometry of spacetime. One of the earliest ideas is that information is subtly encoded in the correlations within Hawking radiation. While the radiation appears thermal at first approximation, more detailed analysis suggests that quantum entanglement between emitted particles and the interior of the black hole could carry information in a highly scrambled form. This would allow the total evolution of the system to remain unitary, even if the information is practically inaccessible to an outside observer. Another influential concept is the notion of soft hair on black holes, a term introduced to describe low-energy excitations at the event horizon that encode information about the matter that fell in. These degrees of freedom are associated with symmetries of spacetime, suggesting that the geometry of the horizon itself may carry an imprint of infalling matter, preserving information in a subtle, non-local manner. The holographic principle, motivated by studies in string theory and quantum gravity, offers a more radical framework. According to this principle, all of the information contained within a volume of spacetime can be represented entirely on its boundary. In the context of black holes, this implies that the event horizon could function as a two-dimensional repository of information, encoding the three-dimensional interior in a manner consistent with unitarity. AD/CFT correspondence, a specific realization of holography, provides mathematical evidence that a gravity theory in a higher dimensional space is equivalent to a quantum field theory on its lower dimensional boundary, reinforcing the idea that information is preserved even when it appears to vanish behind an event horizon. Other proposals involve subtle modifications to quantum mechanics or spacetime structure near singularities, suggesting that information may be gradually released during black hole evaporation, or that our classical conception of the event horizon requires refinement to account for quantum effects. While no single mechanism has been universally confirmed, these approaches share a common feature. They respect the fundamental principle that information cannot be destroyed, aligning with unitarity in quantum theory. They highlight that apparent paradoxes often arise from attempting to apply classical reasoning in domains where quantum effects dominate. The exploration of these mechanisms has profound implications, not only for black holes but also for the development of a consistent theory of quantum gravity, as they offer pathways to reconcile general relativity with the unyielding demands of quantum information theory. In this sense, the study of information preservation is as much a study of the universe's mathematical structure as it is a probe into its most extreme physical phenomena. Winning the bet with Stephen Hawking over the fate of information in black holes is more than a personal milestone. It has profound implications for our understanding of the universe and the fundamental laws that govern it. At first glance, the question of whether black holes destroy information might seem esoteric, relevant only to theoretical debates among physicists. Yet it strikes at the core of our understanding of reality. If information were truly lost in black holes, it would imply a breakdown of unitarity in quantum mechanics, undermining one of the most well-tested principles in physics, and calling into question the consistency of the entire theoretical framework. By demonstrating that black holes do not, in fact, irretrievably erase information, the resolution preserves the internal logic of quantum theory, while suggesting that the universe maintains a hidden order, even in its most extreme regions. This outcome has cascading consequences for the search for a unified theory of quantum gravity. Any successful theory must accommodate both the geometric predictions of general relativity and the unitarity constraints of quantum mechanics, ensuring that information is never lost, even when matter collapses into a singularity. Furthermore, the resolution of the paradox illuminates the subtle ways in which spacetime itself encodes information. Event horizons are not merely passive boundaries but may act as repositories, storing and gradually releasing information through mechanisms such as correlations in Hawking radiation, soft hair, or holographic encoding. Recognizing this hidden structure shifts our understanding of black holes from simple absorbers of matter to dynamic systems with rich informational content. From a broader philosophical perspective, winning this bet underscores the power of mathematical reasoning and careful physical analysis in revealing the deep order underlying the universe. It demonstrates that apparent contradictions between different areas of physics often reflect gaps in our understanding rather than fundamental flaws in nature. Moreover, it opens avenues for further research, including the detailed study of quantum entanglement in curved spacetime, the microstates of black holes, and the development of experimental or observational probes, however challenging, to detect subtle effects predicted by theory. Ultimately, the implications extend beyond black holes themselves. They touch upon the nature of time, causality, and information preservation across the cosmos. By showing that information survives even under the extreme conditions of gravitational collapse, this result reinforces a vision of the universe as a coherent, mathematically structured system where the deepest laws of physics remain intact and consistent across all scales, from the subatomic to the cosmological. In conclusion, the story of black holes and information is a journey to the very edges of our understanding, where the principles of general relativity and quantum mechanics converge and sometimes appear to clash. What began as a paradox, the apparent loss of information in black holes, has evolved into a profound insight about the universe's hidden coherence. Through careful mathematical analysis and a rigorous application of quantum theory to the extreme environments of spacetime, it becomes clear that information is not destroyed but preserved, encoded in ways that challenge our classical intuitions, yet respect the unitarity, fundamental to quantum mechanics. The resolution of this paradox does not merely settle a decades-long debate with Stephen Hawking. It illuminates the deep structure of reality, showing that even in the most extreme conditions, the universe maintains a remarkable order. Black holes are no longer seen as cosmic erasers, but as intricate systems where geometry, quantum fields, and information are intertwined in subtle and elegant ways. This understanding reinforces the notion that our laws of physics, from the microscopic to the cosmological, form a coherent, consistent framework capable of describing phenomena that once seemed paradoxical or inaccessible. Beyond black holes, the insights gained here inform the ongoing search for a complete theory of quantum gravity, providing guiding principles for reconciling the fabric of space-time with the demands of quantum information. Ultimately, the study of black holes teaches us that nature is not arbitrary or chaotic at its extremes. Instead, it exhibits a profound mathematical harmony, one that challenges us to think more deeply, reason more precisely, and appreciate the subtle beauty of the cosmos. By embracing these lessons, we gain not only a clearer understanding of black holes, but also a deeper appreciation for the universal principles that govern all physical reality, reaffirming that information, like the universe itself, endures even in the face of gravity's most extreme forces.